Okay, back to where we were yesterday. We went almost all the way through Tuesday. We had 2 proofs left. And these 2 proofs are conversions from sets of size n to this less than relation. So in here we say that if you have a number I that is part of string n, then we can construct a proof that translating this I into a natural is smaller than n. A bit to remember the definition of this thing. Remember that string is the naturals up to a number n, and this less than relation is built on top of the less than or equal relation. So here we are saying if you select a natural number up to n, then whatever natural number you select, if you translate it, if you translate from the string into a natural number, that natural number is going to be smaller than this n. This is basically a conversion function. Maybe I should start saying, I don't know if anyone wants to go over some of the exercises that we did in the previous days, like if you had any difficulties in particular exercises.
There was one actually that I didn't get to understand. It was line, I think it was line 448 of the Mongo.
What's line? I think it's 48.
I think, for sure.
Is over here?
So,
do you remember the name of the?
Yeah.
Or maybe, sorry, let me complete that. Was it this one, last fact?
It was, yeah, the one in which the commutative one.
Right. So this one here. Was it the second case, I guess?
Yeah.
Okay. Let's do it. So yes, here we need to prove, and this is a bit of a lie, what Agda says now, because it's normalized. But actually, we need to prove is basically what I wrote there, that x plus the successor of y is equal to the successor of y plus x. Here you see that the successor is outside of the parentheses, because that's what it normalizes to. But yeah, so to prove this, we need to. I guess it's a useful observation to do that, to be able to call any induction hypothesis. We need to operate on x plus y, and currently the shape of what we have here does not look like x plus y. So we need to move the successor out of the successor of y, move it to the left side of the plus. And once we do that, when we can use transitivity here, in the proof below we use the equation of Eisenstein, and here we can use transitivity to do this proof in 2 stages. So the first stage is going to go from this guy here to this guy here. So the successor is going to be moved to the left. And once we have that, we have successor of x plus y, and we need to go to successor of y plus x. But because of how addition is defined, successor of something plus something normalizes to successor of x plus y, and the same goes here. So once we get the successors out, we can just call the induction hypothesis on these 2, and then prepend successor. So yeah, we need to go in these 2 stages and we can use transitivity to do so. So when you say trans, you see that this thing is a variable that Agda has created for you. It can be anything, so Agda does not know about that intermediary type. And you see that on the right hand side argument, the same intermediary type is expected. So 581 and 581. So we'll have to first go somewhere that we don't know yet about, and then go from there to the end. And here we use, for the first step, we use this plus stack xy. To go from here, from this thing here to this thing there. And once we've done that, we are left with this. And then we can use concurrence on stack and the inductive hypothesis. Yeah. And yeah, in fact, I can infer some of these arguments. I think this should probably work. Not entirely. It needs a bit of information, but it can infer the rest of the argument. So the underscore on the right of the equality sign means you infer it for me. The underscore on the left of the equality sign, so when you pattern match against something, if instead of this X we have an underscore, it means I won't even give it a name because I'm not using it. So just don't name that argument. I don't know if, yeah. Okay, so go back to where we were. So yeah, in this case, we need to write a translation between fins and less than or equals. And as always, we start pattern matching with fins. If I here is 0, then the natural number of 0 is going to give 0 back. And so we need to prove that 0 is less than or equal successor of m. And that's easy. And in the inductive case, we need to prove that this thing here, as you see, we have successor on both sides. So we can start by using that constructor that adds a successor on both sides. And once we have that, we can let the derivative go. And Agda can solve it for you. Now, the other way around, we start with this relation that says that n is less than m. And what we are meant to do is we're meant to find a natural number up to m, such that, so this is a fin bounded by the natural number m, such that if you were to translate that back to a natural number, you would get n. So we are saying that this thing here is really equivalent to a fin m, but the only difference is that while this thing here uses n to mention what exactly you select, the fin doesn't. So if you're given a fin m, you don't really know what the number of your selection is. So you could have selected the second element, the third, you don't really know, you need to inspect it. While if you're given n plus n less than m, this is in a way, it is a proof that n is less than m, but it's also a way of selecting the number n which is in the range of up to m. So it's in a way a similar thing to a fin m, but it has more information. And here we are saying that we can recover that information out of a fin. So if you give me this, I'll build a fin such that if I translate it to a natural number, you will get this index n. And so we start pattern matching. In this case, this is the first the case where n is 0. Yeah, so we are going to have to give, here we say the selection is 0, and then when we convert it to a natural number, we need to give a proof that 0 equals 0, and we say flexibility. And in the inductive case, yeah, actually we need to transform. So if I call this inductively, you will see that I get two things. I get a selection up to successor of n, and then I get a proof that converting that selection into a natural number equals n. And that is what I get from the inductive call. I need to transform that into a thing up to successor of n, and a proof that converting it to a natural number equals the successor of n. So I need to transform both the witness and the proof about the witness. And we created this thing here, a map on sigma types, which lets us do exactly that. So here we say you can transform a sigma AP into a sigma BQ as long as you give me a way of transforming the witness, and you give me a way of transforming the proof about that witness. And so we are going to make use of that. So we start by using map, and we need to give it three things. One is going to be the inductive call. So here we are going to do this. And then here are the two transformations of both the witness and the proof about the witness. So transforming the witness is going to be easy. We just prevent the successor. And now we need to transform this proof that we get out of the inductive hypothesis into this other proof. And this is just congruence with SAC. Questions? I guess you can go to Wednesday.
Just one thing, did you update the file? Because in the previous one, the thing to less or equal, like the type declaration is.
Oh yeah, you mean for the definition?
Yeah.
Yes, I changed it because I realized it was a silly unnecessary thing. So before this was, I think it's still like that, as you say. Yeah. Before it was this thing here. So I had like given a fin, I will find the natural number such that transforming the fin into a natural number will be that natural number, and that natural number n is less than m. But in fact, as you see, you can just like get rid of this. So this n you are saying is equal to any I, and then using it here, so you can just like get rid of it. You don't really need it at all. Sometimes I make things unnecessary. Okay. So yeah, for today's lecture, I had two things in mind. One is to use types to describe what an isomorphism is between two types. Then proof a bunch of isomorphisms between things that we defined so far. Then introduce what decidability is, and then I'm not sure we will finish this today, but I want to present a small automated monoid solver. So this is, and as you can see, often like doing this equational reasoning style, it's very tiresome, particularly if you have, for example, an equation on monoids and you need to rearrange the parentheses and you need to do a lot of calls of like associativity, congruence, associativity. And so there's ways of automating this, and that's what I wanted to present today. Most importantly, there's ways of automating this from inside Agda. So you don't have to, you can write Agda code that's automated. You don't have to build it into Agda. You can do it from that side. But I guess we start with the isomorphisms. So I use this little type here to describe, to denote an isomorphism between two types. It's written like this. And it takes two types, A and B, and it's a record. It has 4 fields. One is a function that converts from A to B. The other is a function that converts from B to A. And then we show that they are inverses of one another. And here, in this case, I'm using the propositional equality we defined, but that's like, it doesn't have to be the case. You can parameterize this by any kind of equivalence, really. It doesn't need to be propositional equality, but to keep things simple, that's why I did. How does this definition look? Does it make sense? So here, this from and to refer to these 2 fields defined previously.
So you're making the definition that they're going to be inverse, so you don't have to prove it.
Well, actually, this is a definition of what it means to be an isomorphism. And if, for example, I write a function where I expect as an argument to be provided an isomorphism, then if you want to use that function, you'll have to prove that those 2 things are inverses of one another. Yeah, so this is something that you can use as an assumption somewhere, for example. There's another example of an interface below. So later, I was going to introduce it, where I define what it is to be a monoid. So this is parameterized by the carrier set of the monoid, and it has 5 ingredients. You'll have to select the neutral element. You'll have to select the binary operator, and then you need to prove these 3 laws, that these 3 laws hold. Right, so that the neutral element is the identity on the left, the identity on the right, and that you can freely reassociate. And then so that's once you say this is what it is to be a monoid. And then if you want to prove that, for example, the naturals are a monoid, you need to provide these proofs. So in this case, the operator is addition, and the proofs are the ones that we previously shown. So back to there. Yeah, I don't know how exciting this is, but my idea was to remember how we defined some types in terms of this sigma types. My idea was to actually show that some types defined using sigma types and the some types that we defined originally are actually isomorphic. So this is I'll open all of them side by side. So this is this is the sum type as we defined it originally. So it had 2 constructors. one takes an A, the other one takes a B. And this is sum types defined in terms of sigma types. So here, a sum type is a witness that is a Boolean. And if the witness happens to be true, then the proof is going to be an A. And if the witness happens to be false, then the proof is going to be a B. And so we want to show that those two things are isomorphic. And here, we say that this is the type of this definition, so it's going to be the proof that they are isomorphic. We can do something that is called co-pattern matching. So I'm going to pattern match with CC, but I'm going to pattern match on nothing. So I'm going to do CC enter. And what I get is, instead of pattern matching on an argument, I'm going to pattern match on the result. So the result, we need to return a record, and the record has 4 fields. So for each of the fields, we are going to get a definition. So it means that here I need to give the first the definition of the field 2. Here I need to give the definition of the field from, etc. So in the definition of the field 2, I need to transform this sigma type thing into the actual sum type. And to do that, I can accept the value of the sigma type as an argument. So here you see x is this thing here. Here I normalize, you see that the Boolean, and if the Boolean is true, the type is A. If the Boolean is false, the type is B. I'm going to pattern match this. And I get both the Boolean and the corresponding proof. When I pattern match on the Boolean, I get true and false. And then the corresponding proof changes. So in this case, the Boolean is true, so the corresponding proof is A. And in this case, the Boolean is false, and the corresponding proof is B. And so if I have an A, if I have an A and I need to build something of the type A sum B, I need to go in left an A. I have a B, I need to go in right and B. I think you have a question.
Yeah, the first step is Control-C, Control-C, Control.
So usually when you want to pattern match, so that's why it is just, usually when you want to pattern match an argument, it's Control-C, Control-C, the name of the argument, enter. But if you omit the name of the argument, you pattern match on the result. And that's where you get this co-pattern syntax, where if the return type is a record type, you get one case for each of the fields in the record type. So you don't have to do things this way. In fact, you can actually use the constructor of the record type. So in this case, I called it MK make and that, and then give the 4 arguments. And that's exactly equivalent. But because these definitions can be often long, it's nicer to have one per line. And you see that to the left of the definition, we get the field, and these are the projections. And to the right, we get whatever arguments you want to take. So now to go in the other direction, we start with an A sum B, and we need to create this sigma type. So we do basically the same thing. We pattern match, and either it's in left and an A, or in right and a B. If it's in left and an A, we'll say true A. And if it's in right and a B, we'll say false B. Yeah. And then we need to prove that these two things are actually inverses. So if we call one and then the other, we get back to the same point. And because these two are defined by pattern matching on the argument, to prove that they are inverses, we will have to distract the argument as well. We'll have to pattern match on it. So pattern match on A and pattern match again. And so we get this, which is obviously true. And in the other case, we just get to this, which is also obviously true. And same goes here, so this is going to be inactive A, right of B. And it is yeah, I'm not sure how interesting it is to do all of these. One thing I guess, yeah, worth mentioning is that for one of these, you need actually function extensionality. And function extensionality means that we consider two functions to be equal if for any given input they give the same output back. And Agda is an intentional type theory, meaning that by default, two functions that give the same input the same output, they are not considered equal by default. They can be different functions, even if to the same input they give the same output. And sometimes there's reasons why you want that, because maybe one function is really efficient and the other one takes forever to run. So there are cases where you do want that. But yeah, by default, you don't have this law in Agda. You can postulate it as an axiom and you can use it, and that's okay. But because it's an axiom, it won't really compute. So you can't really do things like pattern matching this equality that you get as an output. But you can use it. You can assume it and use it to prove things if you want it. So in this case, for example, we needed to prove this thing here. So we defined products in terms of pi types. So a pi type is a dependent function type. It's defined here. So for every A, it will give you a proof of B of that A. And the way we define products with it is the same trick. We accept a Boolean. If what we get as input is true, then we will give back an A. If what we get as input is false, we'll give back a B. So this is, I am a function, you tell me what projection you want, and I'll give you that corresponding projection. And so we want to prove that, that is equal to our original definition of products. So that's doing something.
Control-C, and enter.
Yeah. And so in the first situation, this is what we have to do. We are given a function that takes a Boolean, and if the Boolean is true, it gives you A. If it's false, it gives you B, and we need to use it to construct this product AB. So we accept the function, and then to take the product, we run it with true first and with false then. And in the other direction, we are given a product and we need to construct a function. So we need to take a Boolean. If the Boolean is true, give back A. If the Boolean is false, give back B. So we can accept what I'll call the selector as an argument. We can pattern match it. And if it's true, we give back A. If it's false, we give back B. And now we need to prove that these two are inverses of one another. In the first case, we get the function, and we need to prove that this function is actually the same as translating this thing into a function. And so we need to prove equality between two functions. And this is where we need extensionality, because otherwise we can't prove equality between functions. So we start saying extensionality. And it takes one argument. You see that now, instead of having to prove the equality on the function, we need to prove the equality that for any input to that function, the outputs of running that function on that input are equal. So we go from defining equality on functions, purely on functions, to for all inputs, the outputs are the same. So we can now accept the Boolean. And here I'll introduce lambdas, which I think we briefly saw before as well.
Sorry, what happens if you don't use extensionality here?
You can't prove it.
Yeah.
Because of how we define things.
What's exactly the problem?
The problem is that one of these things, so we want to show that two things are isomorphic. And one of these things is a function. So in one of the inverses, we'll have to prove that going from that function to the product type representation and back gives you the same function as the original function. So we need to prove equality between two functions. We need to prove that a function f is equal to a function g. And so the only way of doing that is by using extensionality and showing that for every input, the two functions give the same output, because the functions themselves are intentionally not the same.
I understand. So you have the elements are functions, basically from the pi type.
Yes.
So you cannot say these functions are equal by themselves, but you have to use extensionality
Yes.
to test in every element.
Yes.
So to go a step back, a pi type is a function that, given a function and a set, gives you another set.
So a pi type is, so it receives two arguments, a and b, and it is a function, a dependent function, basically. So for every x of type A, it will give you back p of that x. And then we use that to define products by saying, okay, I need to define a product of an A and a B. What am I going to do? I'm going to go from a Boolean, and if the Boolean is true, I'm going to give you an A, and if it's false, I'm going to give you a B.
There is a question.
Oh, sorry. Which keystrokes did you do for the copatrymathy? Yes, so that's, I'll write it here as well. So that's Control C, Control C, and Enter. So by default, if you want to pattern match, by default, and normally when you want to pattern match on an argument, you do Control C, you write the name of the argument and you press Enter. But if you omit the argument, by default, it tries to pattern match on the result. And if the result is a record type, it does the go pattern matching for you. Okay, so going here, we need to prove that these two things are equal on the same input. And the input is a Boolean. So we are going to pattern match on the input and prove that they are equal for true and that they are equal for false. Now, to pattern match on the input, we need to pattern match inside of this lambda. And there's a syntax that you have to use for that. There's actually two syntaxes to make things more confusing. But you can do it in two ways. You can either surround it in braces and pattern match on X, so this will give you true, and it will give you false. And then you give each case. So that is one way of doing it.
For example, you can use here extensionality because you only have 2 elements, but with a larger group, with a larger action.
Well, you would have to do something like an inductive proof or something. But in this case, because also we defined our function just by pattern matching on these 2 elements, so that's how we do our proof as well. So we can use this syntax, or we can use a slightly preferred this where clause, and then give it like this. So it's slightly easier to read, in my opinion. So this is the same. You can either use the curly braces or this lambda where thing. And so in the case it's true, we need to prove this, which is trivial. So just to go back to what we originally had to do. So originally we had to prove this, and this function here refers to the function that we defined here. Because we don't know what X is yet, it can be either true or false. This doesn't normalize away, because here we defined that function by pattern matching on the X. And so we don't know what the X is yet, so we have the function and the arguments as it is. While once we pattern match on that X, so here by doing the lambda where true false, this X is going to be either true or false. So this function is going to compute to the answer either A or B. And so the goal is transformed, and what you get is these equalities that we can prove. So it's often about advancing computation. So if you define a function by pattern matching on an argument, on a given argument, if you want to prove something about that function, you will have to also pattern match in the proof on that same argument, because that's how the function is defined. So if you want the function to advance in computation, you'll have to do that as well. It's getting things unstuck. So if you haven't pattern matched on it, the function is stuck. It can't advance, it can't compute. But if you pattern match on it, it unrolls. Yeah. And in the other direction, we are given the product AB. And in this case, we don't need extensionality, because we go from the product to the function and back to the product. So we are proving the equality between 2 products, and that's okay. But in the other direction, we had to prove equality between 2 functions, and that's why we needed extensionality. So there's a bunch of things you can prove that, for example, this curried and uncurried forms are the same. So that if you have a function that takes one argument and a second argument and returns a C, and if you have a function that takes an A times B and returns a C, those 2 things are basically the same thing.
Here is the clash of names with the curry, or no, because you used curry last time.
I did use, but I think it was on Monday. So it was inside this simple module. And here I open Mondays, but I don't open the simple module. And that's why it doesn't clash, because I haven't opened it. Yeah, I had to set up all this a bit carefully, because we are redefining things once and again. and so I had to avoid clashes. While at the same time, I didn't want to give them different names. So the name spacing in these tutorials is carefully set up. Yeah, so that's we could do that. It's not very interesting. I leave it as an exercise for you. There's also this thing that we can prove that a finite n is really the same as a n less than m for some given n. So basically, these two types are the same. Fin of m hides this selector n, while this one shows it in the type. But they are basically the same thing. And then we can also do things like compose isomorphisms. So if I have an isomorphism from A to B and one from B to C, then I have one from A to C. Do you want to do any of this, or should I just leave them?
The last one.
The last one?
Proposition.
Yeah, okay. So yeah, we need to compose two isomorphisms, which means that we need to compose all of their fields. So we start opening them up from the x and the y. So you see, this is the first argument here, and this one is the second here. It's a bit verbose. I'm afraid. We don't have to actually open them. We could also do use the projections to define to refer to their fields, and maybe let's do maybe that. So if I imagine the result, this will give us the four fields as co-patterns. And in this case, we need to create a function that goes from A to C. If we apply 2 to y, we get a function that goes from A to B. And if we apply it to x, we get one that goes from B to C. So to compose those, we do 2x compose with 2y. So here, these two are projections out of x. So I call 2 with x as an argument, and that will give me the 2 field from the record x. Yeah. And so the same goes for from the other way around. And we need to also compose the proofs. So here I accept A as an argument. And you see that this is what we need to prove. So because we compose the proof, we need to prove that going from A to C, which we do by doing to y and then to x, and then going from C back to A, which we do doing from x and from y, that is the same as just A. And we have a proof in 2 of x. Yeah, we have a proof that this can be eliminated into something, into just the argument. And so we can use that. If you see, we get the same combination here. So we will use that to get rid of this intermediate from x to x first. So we need to go to the middle of the composition. So we need to have several stages in this transitivity. And because I want to go under the first from y, I'm going to use congruence and from y. And now this is what I need to show. And I'll use this from to on x to show that. I'll call it on to y. Yeah, this is the first part of the proof. Once I do that, I need to show this, and to show this, I use the from to of the y isomorphism. And in the reverse direction is kind of the same, and I need to show this. So first, as you see, we cannot get rid of the 2x from x in this case because they are not together. We can only get rid of this. So we are going to do that. And say sensitivity, congruence, 2x. And I need to get rid of this first. That takes 2 from y and the argument is from 6. And then the second stage is getting rid of the 2 from on x. Once I do 2 from x, we have pasted these two isomorphisms together. Any questions so far?
One thing about k-bindings, you, for example, you started and wrote trans, and then somehow trans got out of the hole and you had a hole.
Yeah. How did I do that? Yeah, that's Ctrl+C, Ctrl+R for refine. So if you have a hole here, sorry. So let's say you have this hole here and you write trans, Agda knows that trans takes 2 arguments and returns this equality. And the goal of this hole is this equality here. So if we want the goals to match in any way, we'll have to apply trans to these 2 arguments to get the equality as a return. So to do that, we can do Ctrl+C, Ctrl+R, and we get the 2 arguments for us. Okay, now for something completely different. Decidability. So we say that A is decidable if we can find either a proof of A or a proof of the refutation of A. So we get 2 constructors, yes, which takes an A, and no, which takes the negation of A. And we can also define a decidable inequality, which says that for any 2, so A has a decidable inequality if for any 2 elements in A, we can decide whether those 2 elements are equal. And here I define just as a helper function an eliminator for one of these decidability proofs. So if I know that A is decidable and I know what to do in the case where it is proven, and I know what to do in the case that is refuted, then I know how to get out of there. This is the same as for sometimes, really. I can also paste decidability proofs together. So if I know that A is decidable and I know that B is decidable, then I know that A product B is decidable. And so basically, if they both are, then the result is. If either of them is not, then the result is not. And this is a small example proof. So here I want to show that I can either say this or I can say that on natural numbers. I want to show that natural numbers have decidable equality. And so I get the 2 natural numbers. And my only way of showing that is by pattern matching. So pattern match on one, pattern match on the other. If they happen to be the same, then the answer is yes on reflexivity. If they are not the same, the answer is no. And here you see this is an absurd lambda. So it's the first one you see. And so we need to prove that we need to write a function Jesus. So we need to write a function that takes as an argument a proof that 0 equals the successor of something and returns falsehood. Now, in the theory of Agda, it is built in that different constructors cannot be the same. So constructors are injective. So 0 is one constructor, such is the other constructor, they cannot possibly be the same. So when we pattern match against this proof here, we won't get any cases. And that is this shortcut here. So we have a lambda because it's a function, and we pattern match against the argument, and we get this open parenthesis, close parenthesis for an impossible case. In this case, we continue pattern matching against m. This is a case where they are not equal because one is successor and the other is 0. And this is a recursive case. And here we can do a recursive call on n and m. And this is what we get. To transform that into this thing, we can use this eliminator here. Like the two first arguments are going to be how to transform the positive case and the negative case, and the third argument is going to be the inductive hypothesis. In the positive case, we are given a proof that n and m are equal, and we need to decide whether successor of n and successor of m are equal. So it is definitely going to be the case that yes, they are. And to do that, I'm going to compose yes, and congruence and successor. So to so I'm given this n equals m. The first thing I'm going to do is do congruence with stack. So that is going to be transformed into successor of n equals successor of m. And once I have successor of n equals successor of m, I'm going to use the yes constructor to create a type deck of that. So this is the same as accepting the proof as an argument and then doing this. And this is the negative case, where I'm given a proof that they are not equal, and I need to show that their successors are not equal either. So I'll accept this as an argument, the proof that they are not equal, and I know that it's going to be no of something. And now I need this thing here. Yes, so I need to accept this proof as an argument as well, the proof that the successors are equal. And once I have these two proofs, I can derive a contradiction. I can use the injectivity of successor to go from this proof of successor n, successor m, to a proof of successor of n and m, and then use that as an argument. So I'm going to call this function f. I'm going to call this function f, and I need to give it this proof. And to go there. I think I proved it somewhere. Maybe not. So I need an extra proof that shows that successor of natural number is injective. So I need a proof that says yes, if successor n equals successor n, then n equals m, where n and n are natural numbers. In fact, I think I can have okay, so small tangent there, but I can use that proof and pass it this equality on the successors to get to this equality on the thing without the successors, and then punch it in. And to prove this is just by pattern matching on the equality. Yeah, this is how you prove that the natural numbers are have the decidable equality. Any questions with that?
I'm confused with the notation of the statement of the injectivity successor.
Yes. I guess I should better explain it. So originally I wrote this, and Agda was complaining that it could not infer. So if you go here, you see you get some yellow there, and if you go here, you see that there's some constraints that Agda could not solve. You can click here, and it will move the cursor to where those constraints are. So in this case, those constraints are for the implicit arguments on the equality. And the thing that it could not solve for some reason, I was trying to figure it out the other day, but I couldn't, is that the equality is the natural numbers. I think it should be able to figure it out because I said explicitly that n and m are of our natural numbers. So then we know that successor here is not the successor of fin. We know that it is a successor of natural numbers. So it should be equality of natural numbers. But for some reason, I couldn't figure it out. So the way you can call an operator that is a mixed fixed operator, in this case, equality has 2 underscores. And if you want to call it without implicit arguments, then you just use each of the arguments on either side. If you want to call it, if you want to give it more arguments, in this case implicit arguments, you can just use its full name and then use it as a head, like a normal function, and then you give whatever arguments you want. You're always asking all the questions, I hope.
When you're saying A equals natural numbers, it's meaning that n and m are going to be A's.
Well, it means that successor of n and successor of m are going to be of type none. So if we go back to the definition of equality, you see that it has these 2 indices A, and so in this case to avoid binding A explicitly, we used A as a variable. We introduced A using the variable notation, but this is really disregard to for all A. So here we are passing that extra argument as an implicit argument, saying A is actually the natural numbers, the type of natural numbers. So yeah, you can prove that a bunch of things are decidable. We can prove that strings are decidable. And we can prove that lists are decidable as long as the elements of the list are decidable. So here we take as an argument, I can write this into we take as an argument the decidability on the elements of the list, and we give back a proof that lists are decidable with that assumption. So yes, so sometimes we are in a situation where we have theorems that we want to prove, and they are very easy to prove. I mean, it's basically application of associativity and congruence and transitivity, but they are a pain to do so, because if you need to do all of those steps by hand, it takes forever. And so you don't want to be doing it by hand. And that's what I guess the nice thing you get about doing maths on pen and paper is that you can say this is obviously true. I don't have to like prove it in detail, while here you do need to prove it in detail. And so sometimes we don't want to do that. And that's where we can at least partially automate these things. And here I'm going to introduce a small example that does that kind of automation for equations on things that have monoid laws on them. So basically, if you have an equation with some symbols on both sides, and they are the same modulo associativity on some neutral elements, this thing is going to solve it automatically for you. And so usually these kind of solvers that you write inside the language. So here we don't write it in the source code of Agda, we write it in Agda. And so we need some reflection capabilities. So if you have a goal that you want to prove, an equation of this sort, you first need to what is called quote this equation. So you need to translate this goal you have into some kind of expression or data type that you can manipulate. So something you need to describe it in a language that you can then manipulate and that you can unquote, so reflect back. So those are the steps. I'm going to skip one of the steps today, the quoting part, because that involves like macros, and I don't want to go into that. But the idea is there. So as we saw before, we defined what it is to be a monoid, and now we are going to define what it is to be a monoid solver. So this is a module, and it takes two parameters. So this is a parameterized module. I think it's the first one we see. And the way that behaves is whenever you refer to a function inside of this module, you will need to pass these two things as the first two arguments. So for example, normal form here, it's a type, right? And so if I refer to normal form from outside of this module, I will have to give these two arguments to it. And there's two ways of handling this, for example. You can either pass these two arguments to each of the functions that you call inside this module, or you can open the module with these two arguments, and then everything inside is going to be open for you on those two same arguments. So it's like a partial application of the functions inside this module. And this is really convenient because sometimes you are in a situation where you have lots of functions that they take maybe the same arguments, and you don't want to be repeating them over and over. So you just write a module that takes these arguments as parameters, and then you can just refer to them inside the declarations of the module. In this case, I'm going to take two arguments. One is a set of symbols. So I'm going to take a type that I call symbol as an argument, and this is going to be so in an equation the type to use as symbols. And then the second requirement is the second parameter is a requirement on this set, and it is to say that this set of symbols must have decidable equality. So given any two of these symbols, I must be able to decide whether they are equal or not. So those are the two requirements for this to work. And
out of curiosity, how do you decide the number in the infix?
oh, here. Well, yeah, good question. Like by default, everything is precedence 20, so that's the default that you start with. But then, like if you load things from the standard library, you'll get lots of. Basically, it's when you create a definition, what do you want its precedence to be in relation to other definitions? So what I do is often I try a number and, oh no, this is too high because I want it to be less tightly binding than this other definition. So I'll make it lower, or yeah, so you need to adjust it.
I have an error.
Yes. Yeah, because it depends on what other definitions you have in scope and the precedence of those. So yeah. Ojo de buen cubero. So yeah, then I define a small language of expressions, and this is where I'm going to quote these equations on monoids. So these equations are going to have three things. They are going to have either a neutral element, which here I use, so in the definition of our monoid, I use epsilon. Here, because I'm quoting, you'll see it's often the case in formalisms, that you just give it the same name, but with this backtick, which stands just like a quote. So it's the quoted form of that thing. So I'm going to have quote epsilon, or I'm going to have a variable, a symbol of some kind, and this is going to accept one of these symbols as an argument, or I'm going to compose two expressions. So for example, if I have an equation like, I don't know, let's say I have an equation on natural numbers that says 0 plus a plus b equals a plus b. This is going to be translated into quote epsilon. Each of these pluses is going to be translated into a quote dot. And then each of these symbols is going to be translated into quote and then the symbol. So for example, for this equation, I can use as the type for symbols, I can use the type fin2 because there's only two symbols. And so I can use 0 to refer to A and 1 to refer to B. And I have decidable equality on this. So that is the type of each of the expressions. So that is the type of the thing on each of the sides. And then I have another type that says this is the type of equations, which basically has a left-hand side and a right-hand side. And the way I'm going to solve these monoids is by normalizing them. And I'm going to normalize them into a type that has none of these things we want to free ourselves of. So a type that has none of these associativity problems and none of these neutral elements problems. And that type is going to be the type of lists. So basically, this, for example, this side, it's going to be translated into a list with A and B. And this side is going to be translated into a list with A and B. And the idea is saying, well, if the normalized versions, if for any environment, so an environment being an assignation from symbols to actual values, if for any environment, these two normalized sides give the same answer, then the original thing is also going to give the same answer for any environment. So that is what we want to prove. So I define the normal form as a list of symbols. And then I define this function normalize, which does the normalization. So we start from an expression. If it's epsilon, I just normalize to the empty list. If it's a symbol, I just normalize to a list with that one symbol. And if it's a composition, I just compose two lists. And then we define what it is to evaluate such a normal form or the original expressions too. So to evaluate this thing, we need an actual monoid. So this is this expression language I introduced. It's a quoted form. It's a data type, something that models these expressions. But if we want to interpret it, we need to give it some kind of semantics. And that's where this monoid description comes in. So I need something to do when I have an epsilon. I need something to do when I have a composition. So I'm going to accept that as a parameter, a monoid on that carrier. And I also need an environment. And as we said, an environment is an assignation from symbols to concrete things of that carrier. So this is modeled as an environment is going to be a function from symbols to C, C being the carrier. And once I have that, I define the two evaluations. One is going to happen on the original expression, and the other one is going to happen on the normalized form. The one on the original expression, well, it takes an expression, it takes an environment, and it gives you back something evaluated. So if it's the empty expression, it's going to give you epsilon back. If it has a symbol, it's going to look up that symbol. So here gamma is environment, and it's a function from symbols to C. And it's going to use it to look up that symbol. And if it's a composition, it's going to just evaluate it pairwise. For the evaluation on normal forms, well, we have only two cases: the case where it's an empty list, in which case I give epsilon, and the case where it's a cons, in which case I will evaluate the head and then compose it with the evaluation of the tail. And now, what I want to ultimately prove is this thing here, which is that for any expression and any environment, if you normalize the expression and then evaluate it, it's the same as just evaluating the expression directly. So what this means is that all the meaning of this expression is already concentrated in the after normalization. So I don't lose any meaning by normalizing it. I preserve the meaning of the expression. So this is what I want to prove ultimately. And I don't know if it's worth stepping through the details of the proof, but basically we start by pattern matching on the expression. So we have three cases. In the case where the expression is the empty expression, normalizing it, it's going to give you the empty list. And then evaluating the empty list is going to give you epsilon back. And on this side, it's going to give you epsilon back as well. So this is an easy case. We just say reference. If it's a symbol, normalizing it, it's going to give you a list with just that one symbol. It's going to be x cons the empty list, and evaluating x cons the empty list is going to give you whatever the meaning of x is composed with epsilon. So we have the meaning of x composed with epsilon, and on the right hand side we have only the meaning of x. So we need to apply identity on the right, and this is where we use one of the monoidal laws to prove this. And in the case where we have composition, we need to prove that the way we defined normalization is that normalizing the composition normalizes each of the sides and then sticks them together. So we need to prove that this thing here is the same as this thing here. And we are going to take 2 steps to do so. On the first step, we use this thing here, which proves that composing 2 lists and then evaluating them is the same as evaluating each of them and then composing them, so that this thing distributes. And so we are going to use that to go to this stage. And then from there, we use congruence and the regression, the inductive hypothesis, to get us to the result. it's a fairly relatively easy proof. And then to prove that this distributes well, we use one of the laws that we need is identity on the left, and the other law is associativity. So as you see, we ended up using all three laws provided by the monoid. And it is good that we did, because otherwise it would be worrying, because it means that we don't really need a monoid to prove this. We can do with less axioms. But to be able to do this, we need all of three axioms. It's identity on the left, identity on the right, and associativity. So once we know that this is the case, what we can do is the following. And here I describe what a solution looks like. So we start by normalizing both sides of the equation. So this is normalizing this side, normalizing this side. And so we obtain two lists. And we use decidable equality on lists and the fact that we have decidable equality on the symbols themselves to decide whether these two lists are actually the same or not. If they are the same, so if this normalizing this both sides gives you exactly the same list, then we want to make a promise. We want to make a promise that says that for any environment, evaluating either these two sides under that environment is going to give you the same thing. So that's our promise. Our promise is that normalizing, if you want to check that these two things are the same, it's enough to normalize them, or rather than it's enough, we can do so by normalizing them. And if the normalization says they are equal, then the original thing must have been equal as well. While if normalizing these two things gives you lists that are different, then we don't make any promises. And we can't prove anything because they are not necessarily the same. We cannot disprove it either. So for example, in the case of natural numbers, it is true that a natural numbers addition of natural numbers is commutative. So if we were given, instead of that equation, if we were given this equation, we cannot really disprove. We cannot say this is never going to be the case, because it is the case that naturals, in addition to a monoid, they are also a commutative monoid. So we cannot say this is not going to be the case, but we cannot show it just using the monoidal laws either. So that is why we return top as, so this is the type of our solution. So the type of our solution, and I guess this is where dependent types comes in. This solution thing, it's going to take in an equation, and it is going to give back a type. And if the equation has two things that normalize to the same thing, the type that it is going to give back is a guarantee that they evaluate to the same thing under any context. But if they don't normalize to the same thing, it is going to give the trivial type back. And then we have this solve thing that, given an equation, it is going to return a solution on that equation. A solution being the thing that we just defined. And we start, and I guess I should have introduced with expressions or with clauses before. So this with thing is a way of pattern matching on the result of this expression on the left-hand side of the equals. So I am given both sides, the left-hand side and the right-hand side. I check whether they normalize to the same thing. And then I have two cases, when they don't and when they do. For the case where they don't, we say that we said that the type that I must return, the type that I must satisfy is top. So I can just say TT. Now for the case that they do, we said that the type I have to satisfy is a proof that they can evaluate the same thing under any context. So I am given as a proof, I'm given as an argument a proof that they normalize to the same thing, and I have to construct a proof that they evaluate to the same thing. And so yeah, this is where I use this equational reasoning style. So on both sides, I need to prove that the left-hand side evaluated under gamma for any gamma is the same as the right-hand side evaluated under gamma. And so to go from there to this, I use this correct little lemma that we just proved that shows that evaluating an expression is the same as normalizing it and then evaluating it. So I go from this thing here to this thing here. And then I use the fact that we are given as an argument the proof that they are equal after evaluation to go from normalize the left-hand side to normalize the right-hand side. And with that, I can use this as a way of automatically solving equations on monoids. So as an example, I have defined a monoid on natural numbers using addition. And then here I use it to solve this equation. So this equation, it is of this form. It has some zeros here and there and some parentheses here and there as well. So I want to get rid of the zeros and rid of the parentheses, basically. And well, in this case, I need to do some extra work because I haven't provided this quoting mechanism that you have to do with macros to translate from the type of the goal to an expression type. So remember how we described the expression data type that had like all the quoted terms. We need to translate this goal type, because this is just an equation in natural numbers. We need to translate this into something of our expression language. And here is where you can use macros to automate that, but I haven't. So I need to basically, this, you see, exactly the same as this, only that all the zeros are substituted with quote epsilon, and all the pluses are substituted with quote dot. By hand, instead of by an algorithm. Yes. So we have the left-hand side and we have the right-hand side. And then as the type of symbols, because we have three variables here, I just use fin3. And so I assign to the fin0, I assign one of the variables, x, to fin1, I assign y, and to fin2, I assign z. And then we can call solve on this thing to solve this original goal without having to manually reassociate all the parentheses and call identity. And so this, it still looks pretty clunky, I guess, because you have to go to the thing, but that's just like, it's not necessary. Like the one in the standard library does this for you. It can get better. It's just a bit more work, but it's the same principle, really. Yeah, any questions with that?
But, did you put it at work? I mean, where is the
So how does it work?
Yes, just to see.
Yes, so this is how it works. Yeah, I was like, I did this for my final year project for my undergrad, and I was demonstrating it, and my supervisor knew about these things. He was the one to teach me, but then I was demonstrating it to someone who did know nothing about any of this, and of course it was all inside an editor. So, and the guy was like, okay, but where's the demo? And it's like, this is the demo. And it is a bit anticlimactic. But yes, so when you call this, when you evaluate this solve function, it will first get this expression, it will normalize both sides. And because after normalization, both sides are equivalent, then the type of the goal will transform into this thing here. So if both sides were not equivalent, let's say if I were to substitute this code X for code Y and reload, then the type of this, yeah, it's a function. Yeah, sorry. And then need to get rid of all of this. Then the type of this is stop. It's not the type of the solution anymore, because both sides of the equation are not equivalent. And we described the type of the solution in terms depending on the equivalence of both sides. So if they were not equivalent, we didn't promise anything. In this case, they are not equivalent and we cannot solve. We need this type, but we have this type, so we cannot solve the equation. But when they are equivalent, when they are equivalent, what you get is a proof that for any environment, evaluating these equations under that environment is going to give you the desired result. And so here we need an extra argument now, which is the environment, which is an association, in this case, of print threes to the concrete values x, y, and z. We'll do lambda where and say 0 goes to x, and successor 0 goes to y, and successor of 0 goes to z. And now it succeeds because Agda doesn't complain, basically. So if Agda doesn't say anything, then it's all good. So as far as I am aware, there's in the standard library for Agda, there's a Monoid solver, there's also a ring solver, and I think some other stuff. But if you want like a heavy automation, then Gog is probably better. Yeah, they have a lot of automation. Also, there's a lot of recent work in integrating proof assistance with SMT solvers. So the idea being that there's this automated solvers on common problems, and so you translate from your proof assistant to something that the solver understands. The solver, which is super optimized to search for a solution and blah blah blah, it searches for a solution, and then it also gives you, and this is like not very standardized, but it gives you back a proof for that solution, and then they are working on interpreting this proof into Agda so that you can build a proof in Agda from the proof that the SMT provides. Yeah. I don't have any more material, so I guess that's all for today.
So have you called this solver that they were trying to put together with Agda?
SMT.
SMT.
Yeah, I actually don't know what it stands for, and I should. Satisfiability modulo theories.
Okay.
Yeah. And actually, for example, Lean, I think, has an SMT connection built into it. It's like already a thing. I think Gog also has some bindings. It's on in Agda, it's something that people are still working on. Yeah. Yeah, so this thing, I mean, there's like a bunch of normal of common problems that these things can solve for you.
Okay, thank you.
There's lots of them. One of the biggest one is Z3, so that's the most commonly known.